My discussion today and talk will be discussing abandoned coal mine mitigation in high artesian conditions. So a little bit about the area in which we conducted a pilot program and subsequent mitigation. As soon as she tells you your phone, then the phone rings. It's nice. Anyhow, the area that we worked at is in central Wyoming. It's in the southwest margin of the Powder River Basin. It's a known area for subbituminous coal within the Lance Formation. Room and pillar coal mining is what this area was predominantly known for about 112 years ago. The general strike of this area is about 300 degrees to the northwest, with the dip trending northeast from 8 to 15 degrees. So artesian was obviously the topic of this presentation. So we had about 112 years of accumulation within the mine interval. So it acts as a somewhat of an artificial groundwater reservoir, particularly in this area that we have. So over that time, it's accumulated about 175 feet of elevation head pressure, which is quite a bit. The target pilot area and mitigation area is pretty much where you see this red polygon right here, which is just immediately east of the downtown Glen Rock area in Wyoming. So a little bit about, this is a digital elevation model just to kind of get some bearings. This is the mine right here. This is a mine map in orange. We got the tunnel basically starting from the southwest to the northeast with haulage ways spanning out in between. Our pilot area where we conducted a pilot project was on the farthest northeast extent. And basically the purpose of that pilot was to mitigate a subdevelopment immediately adjacent to that pilot area. So this was conducted in 2019. We were granted permission to conduct this pilot just to test the feasibility of mitigating in artesian conditions because there's a lot of unknown variables at play. The area was about 1.9 acres. And basically, as I mentioned, it was for feasibility for subdevelopment immediately adjacent to that. So a little bit about the aquifer system, the localized aquifer. So there's three aquifer zones that we identified, one unconfined, and effectively one partially confined in the sandstone formation, or Lance Formation within the sandstone, and then one within the mine interval itself. So these are partially confined, so they're not completely confined. So you still get a transfer and permeation of groundwater up through the alluvium and overburden above. So some of the impact of the local hydrology through subsequent historic mining has led to a lot of groundwater issues and subdevelopment and infrastructure. But you can kind of tell when you have a big topographic relief like this, developing a lot of high artesian head pressures has a tendency to communicate up to the surface through fissures and joints. So this has led to a really high groundwater level within the subdevelopment that we worked at. So it's a non-traditional area that we don't generally do a lot of mitigation in. And I think in the past, they left us alone largely because of these artesian conditions. This is about 300 gallons per minute flowing out of the hole right now. Another cross-section of kind of the groundwater effect and how it affects the strata above. So what you have here is any type of roof caving that'll eventually propagate up to the surface, and it leads to a bunch of stress cracking and bedding separation. So raising your groundwater conditions up higher than a natural state. On the left here, if you had complete confinement, you wouldn't have this raising groundwater here. So a little bit different conditions. We had something in between where we had partially confined conditions, but nonetheless, a pretty big substantial increase to groundwater levels within the area we're working at. So what's the risk of this condition? So mine subsidence is obviously a big risk. Propagation of a failure of roof supporting material within the mine. Extended periods of drought, increased subsidence risk due to a loss of confinement and increase in effective stress to the overburdened rock is something that we were thinking about quite a bit as far as the risk condition. Communication of mine water within the overlying strata. which leads to flooded basements and crawl spaces, impact to local infrastructure, and also potential sulfate attack with large sulfate values within the mine water itself, and communication of mine water to the overlying strata. So infilling, so traditional means of mitigation in this type of mine, infilling is predominantly is the predominant means of mitigation. So, however, doing that, you displace a lot of groundwater in the process, which will thus, transfer that potentially to the surface. So that was a big issue that we were looking at. Also, settlement could be triggered through large-scale dewatering. A lot of people will try to think that dewatering might be the answer, but in a sense, you can actually create collapse within the mine interval if you're not careful by dewatering on a large scale. And the other issue is trapped groundwater conditions leading to very high pressure zones, which could have a bunch of issues in itself. So the pilot program we conducted right up here. So this is immediately adjacent from our subdevelopment area that we were targeting. So here we, once again, it was to test the feasibility of mitigating under artesian conditions. We had 7 monitoring wells throughout this area to analyze, what the groundwater conditions were doing over time. These were shallow and deep. So we had some within the mine interval itself and then some shallow, just to see if there was a cause and effect through mitigation. We had about 100 proposed boreholes, basically injection boreholes for grouting that we had on our design initially. We had a grout barrier that we installed basically to stop any type of flow, groundwater flow to our subdevelopment here to try to really isolate it as best as we can. We had a surcharge load cells to simulate footing weights. That was to check any differential settlement that might be occurring over time just through injecting grout under pressure. Differential sediment was something that we were certainly looking at. Effectively, we were trying to mitigate or trying to emulate the same variables we would have been having in the subdevelopment itself. We also had 1 discharge well that we could use to relieve pressure if we needed to, depending on what our pressure values were downhole. And then, but for this project, we injected about 4,900 cubic yards of grout over 2 acres, which is quite a bit of material. This is kind of our borehole layout and where we had our monitoring wells set up at. Our discharge well was about here. So effectively, once we had any high pressure zones, we'd open this valve and that would discharge our water to basically create some equalization within the mine interval. These are where our load cell boxes were. So we tried to create like a worst case scenario, more or less, in this pilot area, just to make sure that we got it right to where, when we actually went to the subdevelopment, we weren't going to be creating a bunch of issues. So as many things that we could kind of throw at this pilot program, we were trying to key into to make sure we could design for all of that. This is a setup of our discharge well that we had. So we just had a ball valve on a ball valve, more or less, for relief of the groundwater. So if we had any type of high pressures, we'd relieve the water up to a certain amount just to create that equilibrium downhole. Kind of trenching, we were graced with the local pond that was near there for discharging. And we had some cloud-based transducers to help us so we can kind of analyze this over time outside in the field and in the office as well. Some more pictures of our traditional setup that we had. There's our valve to open and close, so we'd be able to control the amount of flow out of this well, essentially, to this pond. The chemical conditions in this pond were very, very much the same as what we had in the mine, so there wasn't any contamination issues that we had to worry about in doing so. Let's see what else we got here. This is the type of groundwater response that we had from our wells. So you can kind of see the initial conditions that we started off with as a baseline condition and what we had over time. So this is inverted. So what you see over time is basically decrease in groundwater levels over time. And then you can see each one of these peaks is effectively when we're injecting grout, you'd see it basically cause and effect, peak up and then open our well. and an immediate drop. So you had some lag time associated with the data coming through on the well information. In addition to these monitoring wells over here, we also had some all over town just to kind of see if we could see any correlation with the mitigation work that we were doing there with respect to groundwater conditions. We also had some set up in the neighborhood as well. We didn't see too much deviation while we were conducting this pilot program in there, but it was good to have nonetheless. Once again, this one's not inverted. So basically we got similar conditions, cause and effect more or less through injecting under pressure and then also utilizing the relief well. So this is the first time that we used the relief well. So obviously we had a pretty quick drop. It's something that took us a while to get the hang of, is trying to find that balance of what's too much and what's too little. So anytime we got above a baseline condition, that was kind of our key more or less to turn on that valve and try to just, get some equilibrium within the mine interval itself with respect to pressure. So we used a alternate grouting approach. So the traditional means and methods for grouting is to use a very thick grout, which doesn't have a lot of mobility. We were using a high mobility grout. So very much different. So this works well if you're dealing with rubbleized conditions like we were seeing throughout the town and within this particular area. This grout has a tendency to consolidate over time. Obviously, when you first inject it, you got a lot of suspended solids, but over time, the stuff will self-consolidate and cure. So this is what it looks like within the mine. So we're able to get some good shots of that with the downhole camera. Compressive strength's about 200 PSI. And then we were seeing about 1,200 to 8,000 PSI in situ strengths when it's starting to mix with the rock and the existing material within the overburden. Once again, it's heavier than water, so it consolidates and cures within the mine. And yeah, it's there to fill grout, joints, fractures, and any of the rubbleized conditions that exist. This is kind of a, let's see if I can play this here. This is basically injecting under pressure, just kind of a demonstration of how injecting under pressure works if you have rubbleized conditions. When you add pressure to it, you're able to fill up all these joints and cracks. So the thought being, if you already have subsidence collapse, it's going to continue to propagate. Your propagation could be still occurring effectively above the mine, even though you filled the mine, which is the general approach that they took in the 90s and the 80s. So in 2021, we felt pretty good with the data that we collected and the information we gathered from the pilot program. So much so we put together a design and slated to mitigate this area. So in this area, this is about 14 acres and what we mitigated here. We had about 600 holes with an average depth to 150 to 200 feet below grade. We injected about 25,000 cubic yards of grout, which is a lot of material. Water discharged, we had 6 permitted wells on this corner here. So the thought process and the methodology was to effectively start on the southeast corner and push the grout or push the mine water effectively to this corner right here. If you guys recall, we had a little pond more or less that we used to relieve any pressure. So we were able to push all that mine water effectively down here, which worked out really good. So we had we also had about 2 years worth of baseline studies to kind of forecast, what the groundwater does over time. That was a key set of information for us to really design well for this type of project. Just another map showing where we had our discharge wells. So 6 of them here. These were all within the mine interval. So we were able to see pressure values and how they'd be increasing over time. So once we started injecting grout and pushing it, we'd get immediate information from these wells to either open or close them depending on what those pressure values were doing. So once again, we didn't want to just leave them open the full time and dewater the mine and create a destabilization problem as well. So it was kind of a bit of finesse. We also had shallow groundwaters monitoring wells within the subdevelopment itself. So we started seeing any type of raise in groundwater conditions, that was kind of our key tip-off to stop and reassess with what was going on from the perspective of pressure values and see if we can kind of stabilize some things just through waiting a little bit of time. A little bit more about the discharge well. So yeah, these were installed on the northwest corner, as I mentioned. You're seeing, between 100 to 300 gallons per minute when these were initially installed. These were all fed into a main manifold where we had a 24 conduit pipe running to the pond. So everything was more or less put together essentially. So each one of these wells had its own pipe, and then those would all feed into the manifold and then out through this main discharge point here. We had a little spigot for doing some chemical analysis on the groundwater to see if we were seeing any changes in values. Just a typical detail of that. So we had these installed. These are geocon transducers, piezometers that we had, and some geocon nodes, so we could assess what this was doing anywhere, any office within our company. So we had 20 of these total, not only through our area, but also throughout town. So it really helps us get a baseline as far as what those groundwater conditions are doing during and after mitigation. So yeah, each one of these was set with a vibrating piezometer and wireless nodes. So those were all remote data for monitoring at regular intervals. And then wells were installed in multiple stages in the project. So the key with these wells was to get them at multiple depths, because with the 3 aquifers that we identified, we had different groundwater conditions on each one of those. So these are known areas of concern that were historical. Each one of these houses had some issues of groundwater occurring before any type of mitigation work. This is pretty kind of unprecedented. I think naturally when they built this subdevelopment, they already had high groundwater conditions already. Matter of fact, I think they had to lay some of this infrastructure in place during the winter because the ground was frozen. So they already had some known water issues at the time. So the key was to kind of try to understand that back history first before doing anything on the site. But here's an example of one of the properties. This is water. It's about 6 inches of water that's been sitting in this crawl space for 42 years. So these are the conditions that we were seeing across this whole subdevelopment with respect to some of the groundwater issues that this mine was causing over time. So during completion of this project, we completed it in November 2021, injected about 24,000 cubic yards of grout, and which equates to about 4.9 million gallons of water that was displaced. 5.6 million gallons of water that was discharged through a well system, which is basically the approximate size of that. It's about 8 Olympic-sized swimming pools. Put it in comparison. These are some of the groundwater responses that we were seeing in our different discharge wells. So again, kind of just showing, that the cause and effect through either opening the well while simultaneously grouting and not opening the well while grouting. So trying to find the equal balance was pretty difficult and challenging. We generally had somebody man the valves at all times to make sure if we were seeing any pressure spikes when we got a recorded value that we could immediately relieve the pressure to a certain extent. This is one of our wells that's open right here, feeding into the main manifold. Uh-oh. There we go. So as you can see over time, we saw a decrease in groundwater conditions within the subdevelopment. So this is pretty substantial. This is exactly what we were hoping to see. All those high pressure conditions within the artificial reservoir itself were more or less gone because there was no void space. that was all filled with grout. So there's no confinement of groundwater, increasing groundwater tables throughout the area. So we're still monitoring right now, and we continue to hopefully see a drop over time. But that was a good assessment to see at the tail end of the project. Same thing with shallow groundwater, basically starting at 6 feet below grade, ranging on average around 12 feet below grade. So we saw a pretty good drop there as well. Thank you so much.